I recently had the pleasure of sitting down with an old friend and longtime technology leader. You probably know him, Tim Segedie. Tim and I go way back. In the early TechWise TV days, he was doing yeoman's work convincing me, that QoS is more fun than perhaps I was giving it credit for. We kept inviting him back to the show for multiple episodes, diving deep into the technologies he was driving at that point in time because it kept changing. Tim is not just a technical expert, but a gifted communicator who can break down complex topics for any audience. And since those early days, I've watched in awe as Tim has been at the forefront of multiple groundbreaking technologies, one after the other. He was the architectural lead for Cisco's DNA application policy module, which many of you may know as EasyQoS. That one kind of made sense. As well as DNA assurance. During his IoT days, it was CyberVision and intent-based networking. It seems like I blinked at one point, and when I checked back in with him, he was immersed in the world of emerging technologies and incubation, educating the industry on game changers like Callista and Panoptica for cloud-native development. So he's been all over, but really on these edges of things, which I love. So one area where Tim has really captured my fascination recently is quantum computing. And I've struggled to wrap my head around it, and I kind of stayed away from it, quite frankly. But Tim's coverage of it started, I believe, with Cisco Live Amsterdam last year, maybe either, but he made it so accessible, so engaging. Tim is here to explain quantum computing beyond cybersecurity implications, because we'll talk about that, but exposing us all to the technology itself and how Cisco's positioning itself to be ready as capabilities mature. This is a conversation you don't want to miss. Basically, if there's a transformational technology on the horizon, it's a safe bet that Tim Segedie is already in the thick of it, figuring out how to harness it for real-world impact. I've learned a tremendous deal from Tim over the years, both through our formal collaboration on TechWise TV as well as our many conversations behind the scenes. And I'm thrilled to have him here today to share his insights with all of you. So trust me, you're going to want to lean in on this one. As I was going through, one of the things you said was that I think you said somewhere, there was amazing interest in the quantum topic. This was the first time you had presented this. Yeah. But how long have you been working on quantum mechanics, quantum computing, and networking, and just kind of using those interchangeably to a certain extent? As we get into this, you do it with OutShift. Can you kind of walk me through your history with OutShift and how you got there? Because, of course, I've known you as the guy for a lot of things over the past.
Sure, Rob. Happy to. So I've been with Cisco, which is 26 years now. Actually, I saw something come across my screen the other day, and I did the bulk of that in enterprise networking. We worked on a lot of different architectures, QoS at the time. Yeah. Also then, DNA Center, DNA Assurance. Then I spent time in IoT. And when I was there, that was led by Liz Centoni, who then went on to lead not only OutShift, which is our research, development, and incubation branch of Cisco, to say, okay, how can we take, every part of Cisco does research and development. Yeah. Okay, we don't want to claim exclusive rights to that, but the focus in those initiatives is to make existing products better or existing portfolios better, to say, okay, how do we improve in our networking portfolio? How do we improve in security and
stay within their domain center
as well? Exactly, yeah. Right? Okay. Whereas in our charter is to say, where else can Cisco play that makes sense, that we have expertise, either, adjacent technology domains or even emerging technology domains, such as we're talking about here in quantum. And given that, we've well established ourselves as the leaders in networking, now with this fundamental new paradigm for computing emerging, well, any given computer is better when it's networked together. You can accomplish more. Even powerful quantum computers will be able to accomplish more if they're networked together, but it's so radically different and requires such a paradigm change that we can apply some principles, of course, that we've already learned, but we do have to build that OSI layer from scratch all the way up from, level 1 all the way to the higher layers.
Can I ask you how you got involved with quantum? Were you already with OutShift at this point? Did someone say, hey, who wants to take this? And you drew the stick? Or?
That's it exactly. Yeah. So and Liz had invited me to lead technical marketing for OutShift. So that's what brought me over. And I love working with Liz. And I figured too, it's if you're going to be in high tech, be at the cutting edge. And so that was very exciting to me, and it's been very exciting. And so part of OutShift is Cisco Research. And so that's a dedicated team that, partner with various academic institutions, and we hire. We have quantum research scientists. We have other scientists too, as part of our organization that are researching various emerging technologies. And so that is part of our charter to say, look, it's cool that we're doing all this research, but perhaps we could do more about letting our customers know about it so that when they hear quantum, they don't just think, oh, okay, quantum, who's doing stuff in quantum? IBM, Google, Microsoft, etc. But it's like, hey, you know what? There's a huge problem that is, tandem to computing. It's like, okay, we recognize that, computing is being tackled, and that's great. But at the same time, when we started making computers, the networks are what really then gave that an exponential boost in applicability and practicality and all that. So it's like it's going to be the same with quantum. So distributed computing is one quantum networking use case. Even increased accuracy for sensors is a different use case. Like, for instance, if you had a telescope array looking out into deep space, let's say you had 9 of these telescopes. Right now, the accuracy of the images that are compiled from all 9 of these would be about plus or minus 1/3. Okay, so it's plus or minus n. But if you networked all the information together via quantum, it would be plus or minus square root of n. I'm sorry, let me start again. It would be plus or minus square root of n, current accuracy, which is 1/3. But in a quantum network, it would be 1 over n, so 1 over 9. So the accuracy of all these measurements would be significantly enhanced, including systems like GPS, including any other types of distributed sensors or clocking applications. But, there's even the biggest use cases for quantum is kind of like the double-edged sword that it presents is in cryptography and secure communications, because compute on itself, various quantum algorithms have shown this property called quantum speedup, where they can do things that traditional computers cannot do with nearly the efficiency. Like, it would take them the age of the universe to crack like RSA keys, versus quantum computers that with specific algorithms that are very tuned and can benefit from the unique properties that these provide, such as Shor's algorithm. That's the most well-known one. That has been proven then to speed up the factorization problem. It says, okay, if I have a huge prime number, what were the multipliers that can be used to create that number? Well, that's a very difficult problem for existing digital computers to solve, but quantum computers, tremendous speed up, exponential speed up, in fact, in that particular use case.
But cryptography, it's based on the factoring of large prime numbers that are difficult to do with traditional methods. And so from a compute perspective, it almost seems like, well, this quantum key distribution, which at first I had mistakenly thought, oh, that's the only thing Cisco cares about, because that's all I saw when I looked up in very brief times in the past, go, oh, that's the only reason we care about quantum is because of this. But then as I'm going through this, not only are there many more reasons, but it also made me think quantum solves the problem, but it also created the problem in the first place, right? Because quantum enables you to crack it, but it's quantum that enables you to make it more difficult again.
That's true. So a couple comments. So like there's two main, there's 2 main approaches to cryptography. What you talked about and addressed is exactly correct for asymmetric cryptography, where you have 2 different keys. You have a public key and a private key. And so, that factors, this factor plus that, we combine them and we'll get that, we multiply them together, we get the overall key that will encrypt or decrypt the message. And so that factorization problem, very, very efficient, very, very threatening to nation states, to companies, to even individuals, because this is what our entire public key infrastructure, RSA, and all these other algorithms, Diffie-Hellman, elliptic key, all of that is directly being threatened by the advances in quantum computing, particularly revolving around the use of Shor's algorithm. The other main method of cryptography is symmetric. So AES, Advanced Encryption Standard, is symmetric. And so in this case, then, there is an algorithm that is being looked at and considered, and it's called Grover's algorithm, which basically, finds finds a variable in a database. Let's say you had 16 boxes and you have a red ball in one of the boxes. Grover's algorithm will find that very, very quickly. It will be not an exponential speed up, like a classic algorithm would take up to 16 tries. Is it in this box? No. Is it in this box? Is it sequential? But Grover's will do it with a quadratic speed up. So if there's 16 boxes, it will do a maximum of 4 passes to get that specific location. So then the concern was, oh, does this going to threat AES? And so there's been some confusion in the media and in articles. For instance, back in 2016, some Microsoft researchers published a paper that says, yeah, you can crack AES, but you're going to need like 6,600 logically corrected qubits, which require many, many qubits, 50 or more, depending on the latest configurations each. Mm-hmm. And so this kind of says, yeah, it's a threat, but it's a long way off. But actually, one of our own cryptologists at Cisco, Scott Flurer, published a paper called Revisiting Grover. And he said, look, even if you had the ability to crack it, because it's not a process that parallelizes well, you actually will have to apply a sequential approach that even if you could do each pass in like a picosecond, it would then take you longer than the lifetime of the universe. So long story short, asymmetric cryptography, public key, RSA, all very much threatened by quantum. Symmetric right now, it's with the current algorithms and the current technologies, that's considered quantum secure. Okay. That being said, there's 2 approaches then to solving this, and this is a top of mind issue that quantum presents. The biggest threat and challenge, and actually at the same time, like you said, biggest solution that quantum presents is that it threatens security, but then at the same time it promises security. Mm-hmm. And then here's the way it promises it, because like you mentioned quantum key exchange. So that's a way that you can actually encode a key to share with another party privately. And if you encode it in quantum, then there's a unique property of quantum that is the no cloning theory. And in my slides, I do actually have the mathematical proof for no cloning and why that is the case. But basically, it just logically, it makes sense. It's like for me to copy something, I need to read it. Well, these quantum particles are so sensitive to the environment, to electromagnetic, to temperature, to all sorts of noise, and they're very prone to error, that even the act of reading the state will cause a quantum collapse of what's called superposition. It will collapse this quantum state, and it will just give you an output of 1 or 0. That's very easy to detect. So if somebody has read my key or any part of my key, I can detect that, and I know that if there's been any sort of eavesdropping occurring. So I can protect myself from eavesdropping. It's mathematically proven that if I encode in quantum, I'm mathematically protected. So that's one. Okay. Now, the other hugely mind-bending and super cool element of quantum that I like is the concept of entanglement, right? So you get two particles. Let's say I get 2 electrons, or actually for communications, it'd be more appropriate to say photons. And then these 2 photons, and by the way, entanglement is simple enough to achieve. Basically, if I send one larger photon, a laser, through a specific type of crystal called a nonlinear crystal, it splits it into 2 smaller powered but related photons. They share properties, and the specific properties is that whatever happens to one, say one starts vibrating horizontally, the other one will vibrate, and oscillate in an opposite manner. Like there's some shared property. If it's a case of entangled electrons, if one spins up, the other one may spin down, depending on the specifics of the encoding. But they will happen instantaneously, and regardless of distance that they are apart, and regardless of media. There is no media in between to tap into to say, oh, what's happening between these 2 electrons? So if I make a reading on one, I automatically know the state of the other at that instant in time. And so so no cloning plus this communication via entanglement, where there's actually no media that you can tap into, that presents tremendous potential then for securing communications.
So because you're hitting on a couple of things that make quantum unique, and I wanted to give you permission to go ahead and lay that foundation, because I know it helps to explain Shor's algorithm and Bell state and things like this if we understand. So you mentioned entanglement and no cloning. What's crazy to me is with entanglement, for instance, is how that is not susceptible to distance. It's like, how are they remaining connected to each other? And I understand from deep diving on your presentation that we can't communicate over that, but it allows us to do other things that we're playing with. But do you want to go through some foundational things that may help explain how
Sure.
the challenges that we have with getting it, and why, there's a certain bit of a race, right? To say, how do we get to where we need to go? Because we don't have it all figured out yet, right?
Sure, I'll do my best. I'll do my best. So, like, it's a big,
yeah,
it's a
within
big
reason.
question.
Remember, you're talking to someone who won't
to answer
check
it
you.
simply, but I'll try very simple.
Okay.
So, if we basically quantum is in quantum mechanics is the physics that's applied to the rules of physics that are applied to subatomic particles, that is within the atom. Because it's been noted that, okay, like while we have well-known rules for our physical universe, like Newton's laws, like every action has an equal and opposite reaction, the third law, or objects in motion tend to stay in motion, objects at rest tend to stay in rest, etc. Force equals mass times acceleration. All these laws, we've known for hundreds of years. But then when they looked inside the atom, things were not behaving according to those laws. And so they observed a duality in the nature of these subatomic particles, whether they're photons, electrons, neutrons, whatever it may be. They would exhibit properties that made them look like and act like particles at times, and at times as waves, oscillation and waves. So this dual nature, dual particle wave, this particle wave duality is fundamental to understanding, or at least trying to wrap the head around in understanding.
Because it doesn't change anything we already understand about physics, but it challenges some of the edge cases, or does it change?
It changes the rules of physics at that scale. So there are things that happen in that subatomic scale that break the laws of Newtonian physics, the physics of all larger objects, all the way up to, galactic and universal sizes. But inside the atom, there's things that happen that are unique to that scale. And so some of those properties, like we've talked about a few of them, such as no cloning. If you're trying to read the given state, like we talked about spins of an electron. Let me give an example. So when it comes to computing, the most popular way to represent information, and in the quantum world, information is represented as not bits like we use for digital computers, bits that are a 1 or a 0. It's basically using transistors. All our digital computers based on transistors. There's either a voltage present, in which case we say that's a value of 1, logical value of 1, or there's no voltage present and it's a logical value of 0. In quantum, they use these subatomic particles. For computing, the preferred particle would be an electron. And they'll take the spin of an electron. And again, here's where it's, to be subtle, it's not the physical spin. It's not like I'm just going to be spinning up or spinning down, even though that's how it's described in all the literature. It's actually the magnetic fields. If you think about planet Earth, we have a magnetic field from the North Pole to the South Pole, and that's the direction it flows, top to bottom. But I think it's every 50,000 to 3 million years, for some random reason, it reverses and changes. But with electrons, it not only reverses and changes randomly, and it could be top to bottom, bottom to top, like the north and south will flip. It could be from any direction, even on angles and this and that. But here's where it's interesting. So they say, okay, let's take an electron, and let's say that if the spin is from the top, okay, and let's say a spin, and they'll say, okay, spin up. So I'm going to physically represent a spin up just by actually physically spinning the ball, rather, because I can't really illustrate the electric
Is that a
field
real
very
electron
well.
in your hand? Is that a real electron in your hand?
It's a real electron.
Okay.
I don't know. I just love the visual aid. So
I love it.
So I have an electron, and if it's spin up, we call that state 0, and then spin down is state 1. right? So if an electron is perfectly vertical, think like if we have the planet Earth analogy, if the south pole of planet Earth, you're on the south pole,
Yeah.
that would be a value of 0. I'm sorry, if you're on the north pole, the top, you're at a value of 0. And if you're at the south pole, you're at a value of 1. Okay, that's super. But really, you could be anywhere else on that globe. We are, right? You're in Texas, right?
Yep.
And I'm in Vancouver. So I'm not completely at the North Pole, nor am I completely at the South Pole. I have some degree of north and I have some distance to the south. And so I may be somewhere else on that surface area that has a degree of 0 and a degree of 1. And this is where quantum is different from bits. Rather than just being an absolute binary value of 0 or 1, it could be something in between, a probability of 0, a probability of 1. Kind of like, when you got a coin and you're flipping, that's a poor flip. Let's try that again. Under pressure.
Yeah.
You have a coin flipping in the air. Is it heads or is it tails at any given instant? Well, no, it's kind of both. It might be somewhere in between,
define an instant.
Depending on that instant.
Yeah.
And it's only when you finally take that final reading and then break it down to a single value that you know its final state. So this is similar in quantum. This is to say, okay, there's a probability of this qubit representing 0 and a probability of it representing 1. Now, what becomes really interesting is that when you have more than, so basically for each bit, I'm representing 2 values at the same time, and I'm performing computations on 2 values at the same time for every single bit. Now, when I add more bits to my computer, now if I had 2 bits, 2 here and 2 here, I have 4 values that I'm representing at the same time and performing computations on at the same time.
Hello.
And so every bit that I add to my computer becomes exponentially more powerful in its ability. This is called quantum superposition as well as quantum parallelism, to say, okay, when I keep adding to the system, I'm able to parallel process far, far, far more effectively. And I'll give an example. Like in 2021, the world's largest supercomputer had 133 qubits, and it was stated that it was 150 million times faster for specific operations than its digital counterparts. So what that means as far as time is that if I kicked off a job, say during the golden age of Greece, when they were building the Acropolis and the Parthenon and all that stuff, and then a digital computer would be computing all that until now, and then a quantum computer of that same corresponding number of qubits rather than regular bits would have completed that task in a minute. So it's a phenomenal speed up. But now it's also important to recognize that not every algorithm is well suited to the nature of quantum processing. Not everything that we're going to do and that computers do will be taking advantage of the ability to speed up calculations. Quantum algorithms are very good at solving problems that involve probabilities because of this nature. It could be probability of this, probability of that, and then by a combination of superposition and another property, a unique computing property of quantum, which is quantum interference manipulation. And here we take advantage of the nature of waves. Okay. If you have waves that are perfectly in phase and in sync, and they come together, well, then the result is the algebraic sum of the waves. So 2 waves that are perfectly in sync, they add together, you get a really big wave if you time it well.
And it's a sum, not an average?
It's actually a sum.
Okay.
So if the 2 waves intersect, the resulting value at the point of intersection will be the algebraic sum. And then if you think about it, I think where you're going is that in the case of waves being out of sync, say that I'm going up on one wave, but I'm coming down on the other, and they intersect, then it's a positive sum plus a negative sum, which results in a cancellation. Yeah. And that's actually the principle of our very earbuds. Yeah. In any type of noise cancellation system, will listen to the ambient noise around us and then reverse the phase by 180 degrees and then combine that with what you're hearing around you, and it will cancel, it will flatten that out. So the way that these algorithms are designed to work is that the programmers will seek to leverage this ability of either constructive interference, which will increase the probability of the right answer being manifest, or they will apply destructive interference to cancel out the probability of the wrong answers from having a high probability. And then as they run these systems, the whole intent is that the correct answer will have a probability that is as near, or if it could be 100% probability, if not as near as possible.
Is the idea to get a high probability to then boil it down to where it's either a 1 or a 0? So we're back in the binary.
Yes.
Okay.
Yes, very much so.
And you might use more qubits to do it to increase your probability.
Yes. Okay. So you either use sometimes more qubits, or you might have to do a few iterations, like in the example we talked about with Grover's. So you had 16 boxes where that red ball could have been. And you have, after the first pass, you have decent probabilities for about 8 options, then decent probabilities for 2 options. And then, the fourth pass, you have near unity probability or 100% probability of the final answer. So sometimes it may be the sequential running of the algorithm that gets you that increase, that high level of probability that asserts the correct answer, the most correct answer.
So where does this stand today in terms of not networking, but just quantum computing? It's IBM's doing it. We're doing some things, but is it usable? Yeah. Are people using them yet? Or is it still theoretical in many places?
No. It's actually absolutely usable. And you'll see, pictures of quantum computers in magazines or in labs. They're typically, in these huge 45-gallon drums hanging from the ceiling.
Like an ugly chandelier almost, yeah.
An ugly chandelier, yeah, very good. So they're actually using them, but they're very limited in their capacity. We're talking like, 100 or so qubits at a time. And the challenge, one of the biggest challenge, is this quantum error correction. So it's not like you're leveraging each qubit as a computational bit, but rather you need multiple qubits to help do error correction. So you're not really getting the full value of all 100 or so qubits for pure computation. So it is very analogous to where, say, computers were, say, in the 60s. Okay, we're just starting, some of these systems were very rudimentary, and we kind of laugh at how few, bytes of capacity they had in memory and stuff like that. But there's definite, that exponential increase potential, like that we've witnessed with digital systems, that likely will be even occurring faster with compute, because we've learned a lot of lessons. Like, really, when it comes to computers, we've been doing computation for over 100 years. Like, the vacuum tube was invented over 100 years ago, and that was the basis for the first computer, the ENIAC, the first modern digital computer. And then, transistors in the 50s, right? Integrated circuits, I think they started in the 60s. By 70s, we had like Intel's, was it the 3033 or 4044, something like that. And they started, and they just had ridiculously limited capabilities. Now it's laughable, but then Moore's law kicked in with very consistent effect. Like every 2 years, they were doubling the capacities of transistors on these integrated circuits, and it's the same circuits that we're using, the same logic, right? The same universal gates. All you need is a NAND gate. No, actually an AND gate and then not. So even a NAND gate will simply allow you to do any type of logical operation. You just need lots of them. And then these that's been our approach since. More and more and more and more transistors. I think there's 40 billion transistors in the M3 in this laptop here. So like when you make so many transistors, your capabilities increase.
Well, and that's where,
but with quantum, we're very early,
Well, and so I think it's interesting because I think back, I was reminded of just some, early Cisco days of even translating all the different protocols that used to exist before things settled into Ethernet. Doesn't look like anything I could see in quantum could ever become Ethernet. It's just fundamentally different, but it feels like there's going to be a need for a translation, because classical networks aren't going to go away anytime soon, and how we use them appropriately together to accomplish things. It feels like that was an interesting direction that you were speaking to.
Yeah, absolutely. And the point that you're hitting on is very applicable not just to networking, but even computing. So even quantum computers, they have digital subsystems as part of the computer. It's basically a hybrid computer. It's not purely quantum. Like the final reading is done it's a digital, like when you look for is it heads or tails and you do that final read, that's a digital process. And you're rendering the output as a 1 or a 0, and then a string of these put together, which is analyzed and used digitally. When it comes to networking as well, it's never going to be either a quantum network or a digital network. It's proven, and in my session at Cisco Live, I go through the proof of why you actually need, the physical network. There's some information that cannot be transmitted purely by quantum, as well as then to establish entanglement, you need some physical transmission to happen. So it will always, mathematically always be a hybrid network approach where it will be quantum plus regular digital networking. However, for a quantum computer to communicate with a quantum computer, that path has to be established by qubits. And to transmit qubits, like I just said, though, you need some regular digital transmission to happen, as well as the transmission of the qubit information. So there'll always be a hybrid. It's never going to be a replacement, either when it comes to quantum computing versus digital, which they're already calling classical computing, which I think is funny.
I'm picking up on that just from your
music. Yeah. And then same with networking. So there'll be quantum capabilities, especially when connecting quantum computers to each other, but they themselves will have a dependency on digital communications.
So what are and I know you talked about this, but I can't regurgitate it well enough. So I'm going to try and attempt to do the question, but there's an issue that networking seeks to solve because everybody's focused on quantum, mechanics and computing, which are going to happen in a single location with very controlled distance and environments and everything else. Whereas we're looking at saying, well, the true value comes when you get the network effect. But to do that, there's certain things you can and can't do from a distance limitation. And you mentioned memory, and I think the distance. How do those things work? What's holding us back? What do you think is going to break through first? Yeah,
those are great questions. So the way that we already see quantum computers evolving is, again, very similar to how mainframes evolved in the 60s, where you have these machines are very expensive to build, and you need a lot of expertise. So they're few and far between. They are geographically dispersed. But obviously then, just that's the same with mainframes. If they start talking to each other, you're going to have solutions that are potentially exponentially greater than the sum of the parts. But then what are the challenges into achieving these communications? Well, the challenge is, for instance, there's two ways to transmit information that is quantum encoded. And one is by transportation. We encode a particle with some information, and we try and send that particle. Like right now, when we send fiber optics, we're sending a whole barrage of light particles down a channel, right? So it could be many, maybe hundreds, maybe thousands, I don't even know. But you send a pulse, and then most of them make it through that fiber optic channel. Some will be lost in attenuation, but then on the receiver, they're sensed, and it's like, oh, I received a light pulse, I register that as 1. With quantum, because of the no cloning theorem, I can't send a bunch of photons. I have to send 1 photon with the quantum encoded information, and I send that, and now I have a very high probability of that single photon being lost in transmission. And the longer, the higher the propagation, the longer the distance, the attenuation and the noise is exponentially increasing. So that's very difficult to do.
Like you would traditionally, right?
You can't repeat it. Yes, that's exactly right. You can't repeat it because of the no cloning theorem. So I can't amplify it halfway through and boost the signal.
How do you get around that?
Traditionally. Okay. There's actually some ways around that. So there are quantum repeaters, and we've actually done some work in that and published our findings and research, et cetera, and proven that. But there's an even better solution, and that is instead of using transportation, to use teleportation. So, for instance, I talked about how I could.
It sounds like you're just going to make something up and say our
I'm going to
answer is
make
going to be
something up.
teleportation. Yeah.
The last time I gave a quantum session was just last Monday, and I start the session and I'm talking and I'm going, so I'm going to be talking about quantum technologies. I'm going to be explaining everything in the popular TV show Quantum Leap and how all of these things make it possible to do things like teleportation, faster than light communication, going back in time, and so forth. My audience is just following me. I'm like, is nobody going to call April Fools?
Yeah.
It's like, there's a lot of this with quantum. It's like we're not quite sure what's reality.
Because I learned we can't go faster than light because we're limited to the physical media.
You can't go faster than light.
So we can't break that law.
Absolutely.
Not on the data part.
But entanglement is definitely doable. Like, we do it all the time. So we take one photon, send it through this special type of laser, spontaneous linear down conversion, and that's a process. And then we get two related photons that have this special relationship. We send one of them down the pipe. If it's lost, that's fine. It's lost because there's no data yet encoded on it. And then we repeat that as many times as it takes till we get one of these on either end of a link, a direct link. Okay, once we have it on either end of a direct link, then we encode the quantum information on one using a separate entanglement process. And you can entangle multiple times. The current record, I think, is about 53 that they've been able to push how many times how much your entanglement chain can be extended. And so we entangle this again. And as soon as we do that, then its pair is also reflecting that change that includes the quantum information. And then what we do is we do an indirect reading on one end, and that collapses the quantum state, it collapses the entanglement, but it gives us one of four possibilities of the quantum state on the far end. So then, so then we encode the result of that reading via a beam splitter. We send that using regular digital communications. And that allows us to undo that encoding because it had its original state, then it got encoded. So we're going to try and remove the noise that we indirectly injected and then get just purely the quantum state. And so we don't know what that state is, but we know it's been preserved with fidelity at the far end. And then so every link, we got to do this operation, or even within a router. It comes in on one interface and it will go out on a router or switch on a different interface. Now we have to do entanglement within the box. And this is called entanglement swapping, like a chain. So, one on either end of the link, another pair of entanglement inside the device, and another pair of entanglement on the other end of the link. And we just keep building this chain until we overcome the geographic distances. And then once we have our entanglement chain set up end to end, we do the local reading. And then that breaks the superposition, breaks the entanglement, but at the far end, then that quantum state is preserved with some noise. We do the adjustment to remove the noise, and now we're good.
So how do you think this is?
It's a lot, but it is actually doable. And we have a lab in Santa Monica where it's just dedicated to quantum research. We have as our goal to produce a quantum switch in the next year. We're also doing, even this year, we've already produced a quantum random number generator. So QNRG. So basically, when we do, like, cryptography relies on randomness. The more random something is, the better.
Yeah.
Exactly. So we have pseudo random number generators in traditional systems, but because quantum state is by its very nature completely random, if we do a measurement on a particle in a quantum state, we're going to get a random value of 1 or 0 every single time. And so we're doing this by, a beam splitter taking a look at these the states, and then it's generating true mathematically proven random numbers. And then we already have this as like a rack-mounted system that we're also integrating with a cloud service so that if you need a completely random string, you can get that. And so we're already doing some really cool hardware, software, protocols, and so forth in the research. So it's really exciting stuff.
Is it going to come down to something like because I think of, I don't know why I keep picturing like data center interconnect and you're reading about AI, of course, running out of power in facilities and in locations and needing to, and I always think, well, how would they exchange enough data to be able to coexist with another processing facility in a different physical location? It seems like we're probably pushed up against our physical limits on that now, I would imagine. Is that the type of thing that we're looking forward to, or is it something that I'm not imagining because I'm limited to my
No,
examples
no.
current?
There's several good points that you raised. So a couple thoughts is that, remember we talked about superposition. So for every quantum bit, it's actually representing two values. And then I add another bit, just two bits are representing four values. And so every bit that I add and communicate is actually representing exponentially that much more information. So I actually have this ability to condense information by sending them as quantum bits. So even though the steps are complicated, I have that ability to send phenomenal, like exponential volumes more of information because of the nature of quantum and superposition. Now, the second part, or the point about AI, and that often comes up with quantum. And I'll reiterate the point that it's not necessarily every single digital algorithm that would benefit from the phenomena of quantum speed up. Like quantum computers, because of their very nature, are very good at certain types of problems versus others. Examples like molecule simulation and maybe drug research of how specific molecules will interact with each other, because the reason for that is because nature itself is quantum. So if you have a simulator that's accurately reflecting the nature of these interconnects, then you're going to get a very accurate simulation of it, and then you can get to that problem that you could never compute.
Because now you're making me think of digital twins and kind of taking that further.
Yes, digital twins, but of nature.
Yeah,
of
stuff we can't model right
molecules.
Now. Right.
Exactly. Okay. Or weather patterns, or even like these type of optimization problems too are very conducive for quantum solving. But it's not necessarily that every single process will benefit from the unique capabilities that it brings to the table. And that's called quantum speed up. So not all algorithms exhibit quantum speed up. So as of yet, to best of my knowledge, again, and that's very limited and very new, I've only been doing this about a year. Yeah. But I haven't seen any definitive examples of quantum speed up for AI. The key algorithms that have gained the most attention in the world of quantum is Shor's algorithm, which does the quantum speed up for factorization, which then can be leveraged to break RSA and other public key encryption. Grover's algorithm, which speeds up, it's not the same level of speed up. Like Shor's algorithm is an exponential speed up. Mm-hmm. It can do things twice as fast for every task that you do, whereas Grover's algorithm is a quadratic speed up. So rather than requiring, say, 16 iterations to find the ball in the red box, it only required the square root of 16, 4 iterations. So it does have speed up, but not quite at the same scale. So the point is that not all quantum algorithms are suited to all tasks that current computers use. Mm-hmm. And some that exhibit speed up have a greater degree of it than others. And so this is all, new areas of research. There's probably going to be a lot more of these algorithms that will be coming out, and people are developing them. Those, by no means are those the only ones, but those are just the most famous because they have exhibited the greatest speed up potential.
This is a little bit of an oddball question. I don't know if you'll have examples for this, but I assume they exist. It always feels like we discover when you're pushing for, like, as we used to say with Google, the moonshot of quantum networking, perhaps. Yeah. And in the process of doing that, of course, you have to learn, you got to research, you got to test, and you got to fail a lot and things like this. Has any of that process brought additional capabilities or learning to more of our traditional things? It made current cryptography better, or it made something else come along more quickly.
Oh, yeah.
How is
Absolutely.
it? So there's not just pure about an end result that we're still not going to see. It's raising many other ships, I would imagine.
Yeah, that's a great point, because think about this whole, like when people then hear of the threat to PKI and the threat to cryptography that is posed by quantum, then that's led to a whole new area of cryptographic research in post-quantum cryptography, PQC. And it's led by the National Institute of Standards and Technologies in the U.S., by the conjunction with the government, the White House. And so that's led to a whole new set of cryptographic research and development that is then very difficult for quantum computers to unravel in the way that they are proving for here. So that's a very indirect benefit, and it's beneficial to us right now. And it's an offshoot of the research that is primarily being done in the quantum computing and algorithms themselves. So absolutely, you're going to see a lot of this type of, here's an ancillary benefit that we never considered, or here's something else. And we're going to see a lot of that.
Well, okay. So what does, what do we do with this today? Are there recommendations that you have for students or for people in career, building on their careers? What does this change in terms of what they should be studying, or kind of what we should be watching out for as we move forward for things to take root, or something today we should get more aggressive about? Any idea on what to recommend there?
Well, what I'm aiming to achieve is quantum awareness with our customers. And so to help them understand some of the basics, to understand to be quantum literate, and that also involves some math. I know I had some
trying to skip
my
math.
last Cisco live. So exactly, I am too. I'm like, this is stuff that I haven't done in decades, but you're not going to read any paper or even many articles without quickly hitting some math. So, and that is the most accurate, powerful, and flexible way to express these quantum phenomena. But so I'm personally charging with trying to raise the quantum awareness of our customers, because that's then fundamental to appreciating what we're doing in this space and why we're doing it. We have cryptographic expertise, we have optical expertise, we have networking expertise. When we're starting to do this type of entanglement swapping, we're already observing that basically what this is like a pattern of switch virtual circuits. And I'm like, switch virtual circuits?
I know that.
I haven't dealt with them since my CCIE days, like 20 plus years ago, but it's kind of come around in relevance again, because you got to set up this, this switch virtual circuit to achieve this distribution of entanglement from the source to the receiver all the way through. And then that may have to change if there's a link outage, etc. So it's just, we're very well positioned given all of these strengths that we have, but it's hard then to communicate that with our customers without maybe setting some foundation and groundwork. But I think that it's important to do so that they recognize us as a leader in this field, as a technology partner that's not only here to solve their problems today, like we're doing the advances with post-quantum cryptography as an example of what we were just talking about, but then also providing them, and we'll be the leaders for quantum networking solutions as these evolve in tandem with quantum compute.
There's nothing else that is challenging that as a direction of where things are going, is it? In terms of, because there's always something where we're doing for speed increases, bandwidth increases, or whatever it is that we need to tackle next. Those things always, seem to come along. But this feels like a very big change in terms of where we've been.
Yeah.
And they're going to have to interact. A leap. That's a quantum leap, if you will.
Quantum leap.
Just go back and look that up now. But is there anything else? Is there any other direction that's being pursued in terms of offering similar benefits, or is quantum is that next big leap that probably needs to be made for networking and compute?
In the context of cryptography, I would say, there's the PQC, post-quantum cryptography, to say, okay, look, we have two ways that we can secure your key exchange. One, we can use a pure quantum method, quantum key exchange, because like we said, if you send these, the keys in as quantum bits, and if somebody, and they're transported across physical media, optical cables, But if they're transported, they're subject to eavesdropping. But if somebody reads them, we know it.
Yeah.
We can detect that and therefore mathematically prove it's impossible. So quantum key distribution is one way we can get our keys to each other safely. Right now, using quantum technology, it's viable, it's commercially available. But that requires a significant new investment of hardware, software, out-of-band channels, private channels, etc. But PQC, post-quantum cryptography, says, oh, why don't we just change, instead of an asymmetric cryptographic approach, let's use something different that quantum computers are not a threat to. And so, we're going to present you a solution that's much easier to implement and can already run on your hardware and your networking platforms today, and give you that benefit today, solve this problem today, or protect your organization, because it's not just the threat that will happen in the future when quantum machines quantum compute becomes viable to real-time decryption. That's what they call Y2Q, or years to quantum. And so there's different estimates as to how long that will be. One of the studies, about 80 experts, they target that at about 15 years. But so it's not just that threat when that happens, but there's already this store now, decrypt later type of attack, or harvest now, decrypt later, where nation states are already just collecting all this encrypted stuff that they can't read at all. But they figure, hey, why don't we start collecting it so that when we're able to read it, we'll know all of their secrets from the last 15 years type of thing. So to protect yourselves against that, PQC, implementing that right away, so that, okay, even on our current networks, on our current communication systems, you're staving off this threat. It's very valuable and practical, and it shows that an alternate approach. Now, quantum has a lot more promise than just PKI, like key exchange. Key exchange is just one of the simplest use cases of quantum, but distributed quantum computing, that's going to be the really huge ones, as well as many of the other ones I mentioned, like distributed sensors, or even it can increase the accuracy of our GPS systems by orders of magnitude. I think by 30,000, it's been proven by the IEEE. So that kind of accuracy, like hyperlocation via GPS, all of these advantages, so many use cases for quantum. I don't see anything that threatens that, because it's so fundamentally different than our current systems today, and requires such a radical difference and approach and thinking and computations and programming and hardware, etc. But it has tremendous promise to tap into. I do see that as technology, like, people sometimes get impatient, and then it's good to recognize how computers evolve too. Like I said, like vacuum tubes 100 years ago, we had, some rudimentary machines, in the 60s that we laugh at, and then people say, well, computers, they're going to take over the world. And then people say, but they've been talking about that for years, but then it actually happened, and I think that the development and evolution of quantum compute will be that much faster, given the lessons learned in our first foray into compute, which was based on digital systems. And then it will then expand even more possibilities to us. And I don't think there's anything that has the capability to touch it in these specific areas where quantum speed up has been observed.
I want to end the formal discussion there. I'm going to recommend, I'm going to put a link to your presentation from Cisco Live Amsterdam, is where I came across it. I'm sure you're doing another one coming up in Vegas.
Same at Cisco Live in Vegas in June.
Yeah, and I bet you keep iterating. Exactly, you keep building on that. Yeah. How fun is that too, as a speaker, to continue sharing the knowledge and getting even better at your examples and everything else. But I must say, I just want to compliment you on the fact that you made it very accessible, because even just skipping over Ket, and I forget what the other one was, some of the new terms that remind me of a Greek fraternity or something.
Oh.
With the symbols and everything else, even skipping that, I still understand, I feel like anyway, which is kudos to you, the concepts. And I can begin to see the parallels of what we know today, because I think, how do we take, that's the fundamental thing of learning, is taking something we already know and then using that to extend our knowledge into new areas. But we have to have something to anchor onto. And I think you've done a good job of kind of anchoring those things, those concepts. At least I feel like I'm doing it, and I haven't completely fallen on my face trying to talk to you here. But it's a great presentation, and I know it's going to get better. And it's also fascinating and helpful to know that Cisco is involved in a lot of different things that have nothing to do with acquisitions or something else. Now, we may acquire someone that does something we would find helpful in this. I'm sure that will happen. That's not a problem. But I think it's interesting. There's a lot of R&D going into this, and obviously a significant expense to be able to do it. But I'm glad they've got you at the helm.
$multi-billion investment.
Yeah.
No, I'm not at the helm.
Well, you're the TME over the,
part of the team.
You're the evangelist.
And I really appreciate the feedback. But I wanted to share what I found too is with quantum, be patient with yourself too. I by no means feel that I mastered this. I'm studying. I'm actively doing additional training almost every day, and I got online lectures and So it's a process, but even if you don't catch it the first time, you begin building. Maybe I understand one concept, and then incrementally, there's another aha moment. It can be very frustrating at times because it's so paradoxical and so foreign to our concepts of the real world, like this entanglement. How can that possibly exist? There's no mechanism. There should be some way to communicate that. How is some things we don't fully understand yet? Exactly. That's what
Einstein
called it back in the, I think, 36.
That's what I couldn't remember.
Paper, and it said it's spooky action at a distance. And that's only recently been proven. Like it was 2022 that Nobel experimental physicists proved that entanglement was actually happening. And it's like, and they were able to prove the nature of entanglement versus Einstein's flawed interpretation. Goes, there must be something that we're just not able to measure that's happening. And that's what we're missing in understanding this spooky action at a distance. But basically that was his interpretation. And then there was this famous mathematician in the 80s from Northern Ireland, John Bell, and he had a different interpretation. And he goes, no, that's not correct. And then in 2022, it was these experimental physicists that says, no, John Bell's interpretation of entanglement is correct. And this is actually proven now. And they won the Nobel Prize, but it's very recent. It's just like less than 2 years ago. So this whole field of study is still, at its infancy. And so it is very exciting. So be patient with yourself. Sometimes it's frustrating and paradoxical, but it's good for us to know because it will become as significant as a technology as digital compute.
Well, thank you, Tim. I appreciate your time on this, man. Yeah. As always, it's fun.
My pleasure. Absolutely. Anytime. I love working with you, and it's been a long time, and I look forward to these always. So any time in the future too.
Very cool. Thank you so much.
Good.